Today, we're going to look at Chapter 18 Electrochemistry in Review. And we're going to use CENGAGE homework. Let's see. Get rid of this stuff. Okay. Yep. All right. So what I'm going to do is share the CENGAGE page, and we're going to look at problems that were not assigned. So this is consistent with what I've been doing the past, I think, 3 times. Let's see, there it is, CENGAGE. And there we go. So on the left, we're going to look at difficulty level 1 first and work down through those and go back to 2s and then 3s. I don't think I've assigned any 3s for the homework, but the 3s are instructive. And sometimes the difficulty level 3 that they assign that value, they're not really that difficult. So I'm not sure why they call them more difficult than others. So let's look at this first one. And scroll down. Let's see. Let's scroll down here. There we go. It's got several parts to it. What was this one? I forget. So soon, I forget. 1805. All right. So we got 1805. All right, part A. We have for the following oxidation reduction reaction, which element is being oxidized and which is being reduced. So this is one where you select more than one. So which one is being oxidized, which one's reduced? If we're reacting fluorine gas with copper solid, and we end up with that's also a solid. What we have to do to determine which one's oxidized and which one reduced, we already know it's an oxidation reduction. One reason is they tell us, and the other reason is, remember their rule, that trick. If you got an element here and it ends up in a compound over here, that's an oxidation reduction. Or vice versa. You know, if we just flip the reaction, as long as it's an element on one side and compound on the other, then you know it's oxidation reduction. But in this case, what are the oxidation states of each of the elements as reactant and product? Pure elements are always 0. In their standard state, which would be diatomic fluorine and copper metal, they're 0. So what happens to them over here? Well, the rule is that fluorine is always -1. Right, so now we can deduce what copper is, because 2 times -1 is -2, so that means 1 copper has to be +2. Now we can tell which is which. If you go from 0 to +2, that's an increase in oxidation number. And another way of saying it is copper has lost 2 electrons. Sometimes I write it like this. Lost 2 electrons per copper. And then fluorine goes from 0 to -2. That's a decrease in oxidation number, which means fluorine has gained electrons. Now, it gained 2 total, but each fluorine gained 1 electron per fluorine times 2 of them equals 2 electrons. Some kind of hair on my, yeah, there we go. Okay, so now we can say, remember oil rig. Oxidation is loss. So copper must have been oxidized. Okay, that means fluorine had to be reduced. They always come in pairs. Fluorine is reduced. Okay, that one's correct. This one should be fairly easy to do. The B part. We're reacting fluorine again. Oops, not iron. Chlorine with calcium. Oops. Cation first, correct? Calcium. Fluoride. This looks like it's similar to that one. Right? This one's -1 and this one's +2. These are both 0. Okay. So calcium had to be oxidized, and fluorine then would be reduced. All right, let's see if this one's any more difficult. A little bit. It's worth looking at. So this is C, and we've got iron and oxygen. And that's 3 and 2. Okay. Is that balanced? Let's see, we have 4 irons, yep. 6 oxygen, yep, it's balanced. These are both 0 oxidation state. How about these? Which one are we going to start with? Well, iron can be multiple charge, right? Iron is a transition metal, so it can have different charges. Oxygen, though, we take, when oxygen combines with a metal, a non-metal with a metal, we take oxygen as -2. So that means a total of -6. That means we have to have a +6 over here, but there are 2 of them. Right? So that's +3 for iron. So which one does which? Well, if 0 goes to +3, we're talking about a loss. 3 electrons per iron. Well, times 4 equals 12 electrons. Just being thorough. You don't have to know that to answer the question, but I'll do it anyway. And then this oxygen does what? It gains electrons. Gain, what? 0 to -2? 2 electrons per oxygen times how many? Looks like 6. So the same number of electrons were transferred. That proves also proves that it's balanced. Okay, so which one's which? Oxidation is loss, so iron is oxidized. That means oxygen has to be reduced. Okay? And we've got one left. D. Okay, barium and iodine. Barium solid, iodine gas yields barium iodide, and then probably 2, yeah, 2. and this is a solid. Okay, these are both zero. What happens? Well, let's see. Iodine goes from what to what? When you're faced with this possibility, iodine is a halogen, so its most likely oxidation state in an ionic compound is a -1. Plus, barium is an alkaline earth, which means it's always +2. So either way, you match them up, right? So we have 2 electrons here, 2 electrons there for each. Iodine is gain, right? 0 to -1. Gain 1 electron per iodine times 2 equals 2 electrons. And then barium is a loss. It goes from 0 to +2. Lost 2 electrons per barium times 1 equals 2 electrons. Okay, so oxidation is loss, oil. Barium is oxidized right there. That means iodine has to be reduced. There we go. Okay, so now we can go back up. Let's see, I need to scroll up a little bit. Let's see if 17 is any different. That's too easy. Cesium fluoride. Hydrogen fluorides. Okay, we can do these. There are a couple of easy ones in there and then a little more difficult, so there might be something to gain from it. A, B, C, D. We'll just do them all together. All right. There should be a D down there. Cesium fluoride. Second one is hydrogen, and hydrogen fluoride, and then the big molecule, H2SeO3. That, by the way, is selenous acid. Okay, cesium fluoride. Fluorine is always -1, so cesium has to be +1. In addition, cesium is an alkali metal, so it's always +1. So really, there's no big deal there. What's the oxidation state of cesium? +1. Okay? And there it gives you all the rules. How about hydrogen? Well, that's an element. Right? Hydrogen's always diatomic in its standard state. So hydrogen's going to be 0. Okay. How about HF? Well, in most cases, hydrogen is +1, but we confirm it because fluorine is always -1. Right? Sometimes hydrogen can be -1. Right? When would that happen? Well, if you combine hydrogen with a metal, like lithium and fluorine. Now lithium is +1. Oh, excuse me. Lithium hydride. Then hydrogen is -1. But in this case, fluorine is a -1. There we go. Oxidation state of selenium. So we're looking for this one right here. Okay. Hydrogen we take as +1. That means it's plus 2 total. Oxygen is minus 2, which is minus 6 total, correct? So together we have minus 4. Okay? In a neutral molecule, all the oxidation states must add to 0. So you can think of it as canceling that minus 4 with a plus 4. Right? So a plus 4 and a plus 2 is a plus 6, and a minus 6 is 0. So selenium is plus 4. There we go. Okay. Let's go back up and see if 25 has anything to offer. All right, 25. Okay, this is worth looking at. So A, what is the oxidizing agent? Right. The oxidizing agent is always the reactant that causes oxidation. So if it causes oxidation, that means whatever it's oxidizing has to lose those electrons, and the oxidizing agent gains the electrons. Okay, so the oxidizing agent is always reduced. Okay, let's see which one of these matches. Molecule, atom, or ion that causes the protonation. Now, we're not talking about protons here. We're talking about electrons. Right? So this first one and this last one that says deprotonation, those are invalid. It has to be one of these two in the middle. So, a molecule, atom, or ion that causes reduction. Now, if it's reduced, then it causes oxidation. Right? So it has to be this one. Causes the oxidation of some other species while itself is being reduced. That's true. What's a reducing agent? Well, it's just the flip side. And it's kind of like oxidation and reduction always occur together. Oxidizing and reducing agents always occur together too, for the same reason. So reducing agent is a molecule that causes the reduction while itself being oxidized. That one right there. Okay? All right, let's scoot back up here and see what's next. Skip 3 and we'll come back to that one. How about 18033? Okay, we can do this one. It gets kind of repetitive. But it's like I've always said, boredom is your friend. If you're bored working these problems, that means, okay, you've probably worked enough of them. You can move on to something else. Pennies in the United States nowadays consist of a zinc core that's been plated with a thin coating of copper. Now, why would they do that? It's called debasing your currency. It's making your currency worth less than the actual metal it's made of. So, actually, it's the other way around. the metal you put into your currency is worth less than the value you assign to the coin. And it repeats itself through the centuries. Every government, everyone, without exception, always eventually debases their currency. Okay, so zinc dissolves in hydrochloric acid, but copper does not. Right? So if you drop a modern penny into hydrochloric acid, nothing happens. Right? Because the zinc is underneath the copper. But if you scratch the surface of the penny, then the acid can get at the zinc underneath, and it gradually eats it away, leaving only the thin shell of the copper on the outside. And this is the reaction that it undergoes. Zinc metal plus the hydrochloric acid yields zinc chloride, which is soluble, so it comes out into solution, plus hydrogen. So when you drop that penny, scratched penny, into hydrochloric acid, not only are you going to dissolve the zinc, but you're going to produce hydrogen gas. So you should see bubbles forming right where you scratched it. All right, so for this reaction, the question is, identify which element is oxidized and which is reduced. Right? So if this one is 0 oxidation state and that one is 0, what's this one? Well, this one's +1, this one's -1. This one's -1, and this one is, right, -2, that means +2, so +2. So if we go from here to here, we are oxidizing. And if we go from here over to here, we're reducing. Right? This way we know that chlorine is just a spectator. Right? In some reactions, chlorine changes oxidation state, but not in this one. Okay, so zinc is oxidized and chlorine is reduced. No, not chlorine. Hydrogen is reduced. There you go. Zinc oxidized, hydrogen reduced. All right. Let's see. How about 35? Does it have anything to offer? That's an interesting reaction. If you drop magnesium into water, just pure water, nothing happens. Let's see, 35. Well, nothing happens very quickly. But if you, actually that's not a liquid. If you place magnesium in steam, then you get a very vigorous reaction between magnesium and water that produces magnesium hydroxide and hydrogen gas. All right, so how do we know which one's which? Well, you can just go through and just muscle your way through the problem. Magnesium is 0 state, hydrogen is 0 state. Over here, hydrogen's in water. So hydrogen, there must be something happening to hydrogen. right? We start off here with +1, and here's -2. So +1 to 0 is gain 1 electron per hydrogen, times 2 equals 2 electrons. Over here we get magnesium. Magnesium is loss, because this is, remember, that's a polyatomic ion, OH minus. So there are 2 of them. That means this is +2. Plus magnesium is an alkaline earth. It's always +2. So we have a loss, 2 electrons per magnesium, times 1 equals 2 electrons. So now we know what's what. So what happened to this other hydrogen here? Well, only one of those hydrogens gained electrons, was reduced. The other hydrogen maintained its old oxidation state, right? +1. This is +1. This is -2. That's why that total OH polyatomic ion is always -1, because that's -2 and that's +1, and the difference is -1. Okay, to answer the question, identify the element that's oxidized and reduced. So oxidation is a loss, magnesium is oxidized, hydrogen is reduced. Right there. Okay. Let's scroll this up a little bit. See what 37 has to offer. Oops. That's not right. 37. Here we go. Let's see, am I still on camera? Yeah, there we go. Okay. Only one part to this one. In what 2 respects must oxidation reduction reactions be balanced? Select all that apply. Well, all that apply, there should be 2 answers, correct? In what 2 respects? Kind of giving that away. So, oxidation reduction reactions must be balanced in the transfer of electrons, which in this case they're referencing as charge. So you have to balance the charge, and you have to balance the masses, the number of atoms of the elements, right? And that means mass, right? The law of conservation of mass. During a chemical reaction, mass is conserved. The mass of the reactants equals the mass of the products. So we should have mass conserved and charge conserved. Okay? So this is the part that equals mass. All right, that was 37. Let's see. 37 come down to 63. Okay. That's interesting. I may have mentioned it in class. When Louis XIV right? If you remember your history, European history, Louis XIV was known as the Sun King of France. Everything in his royal presence glittered, right? Gold, silver, whatever it took. But there was one metal that was even more precious than gold. Excuse me. I'm trying to think. I'm thinking back when Louis XIV. I may have my stories mixed up. That's for illustrative purposes. Let's just assume that aluminum was available as a metal in those days. May have been Louis XVI. Anyway, if you wanted to impress your guests at a dinner party, you didn't serve them with gold or silver or platinum flatware around their plates. You brought out the fine aluminum. It was so expensive to produce aluminum that it was more valuable per pound than even gold or platinum or silver or any other precious metal. Now, why is that? Well, the fact of the matter is, it takes a lot of energy, chemically speaking, to convert the aluminum ore into aluminum metal. Now, let's see what our options are. Aluminum is covered by protective oxide. Well, that's sort of indirectly true to answer the question, but it's not the main reason. Native aluminum does not exist. Well, that's true also. Well, no, there are some deposits of native aluminum, but they're very rare. Aluminum is like silver and platinum. What does that mean? That means it's rare? No, it's not. Aluminum is very common. It's an extremely common element. Aluminum is very reactive, and it's not easy to reduce it from the ores. That is absolutely true. So, prior to, name escapes me. Shoot. I'm going to find out. Since we have the time, and my mind won't cooperate. Aluminum. Here it is. Hall. Charles Martin Hall, the Hall process for producing aluminum. In fact, Hall invented the process for converting aluminum ore into aluminum metal while he was an undergraduate. Actually, he started working on it when he was in high school. Then he went to college and continued his work and eventually perfected the process. It was modified later by, let's see, Hérault, which I assume is a Frenchman. And it used oxidation reduction in a more direct fashion. You can produce aluminum metal by chemical reaction, but it's very expensive. That's why, for the longest time, it was more expensive than gold or platinum. But with the Hall process, he was able to directly inject electrons into molten aluminum oxide and reduce aluminum. So the net reaction would have been, right, if aluminum oxide is this, then the net would have been this, and he would have added 3 electrons, yielding aluminum metal. So that's the net reaction for the whole process. The thing about it is, you need a very cheap source of energy, electrical energy, right, in order to do that. If the energy costs a lot to produce, the electricity, then this becomes prohibitively expensive. So that's why aluminum smelting plants were established, like Alcoa aluminum was established in areas where energy was cheap, like in southwestern Pennsylvania, where you have lots of coal and you can generate electricity easily there and cheaply to push that process. Another location is Tennessee Valley. The government paid for all the electricity in the Tennessee Valley. When they electrified the Tennessee Valley by placing dams periodically on the Tennessee River and generating hydroelectric power, they sold it at a loss. I mean, the government could afford to build the dams and set the thing up, and then they just turned it over to the, well, it was actually a cooperation, Tennessee Valley Authority. But the power was dirt cheap. So aluminum smelting plants were also set up in those regions where they could access that excess power. Anyway, that's the answer. Aluminum is extremely reactive, and it's not easy to reduce it from its ores. Okay. Let's see what's next. 63. 65. Is that different? Reactions in which one or more blank are transferred between species are called oxidation reduction. This is definition, right? I don't even need to write that one on the board, but I probably should. 65. By definition, electrons are transferred between species. That is oxidation reduction. If you transfer electrons, that is a redox reaction, oxidation reduction. Just the definition. All right. How about 67? Reduction may be described as, well, reduction, oil rig. Reduction is gain. Right. 67. All right, oil rig. Reduction is gain. Right. So reduction may be described as a gain of electrons or a decrease in oxidation number. It's getting more negative because you're adding negative charges. So that's a decrease. Come on. There we go. Let's see. '69. The sum of oxidation states of the atoms in a polyatomic ion is equal to blank of the ion. All right. 69. This is one of the rules. If you sum the oxidation numbers, they always equal the charge. On the molecule or ion. So, if the charge is 0, then they have to add up to 0. If it's a polyatomic ion, like this problem, then they have to add up to the charge of the ion. Overall charge, right there. Okay? An oxidizing agent causes the blank of any species. I think we already covered this one. An oxidizing agent does what? Well, it causes the oxidation. That's why it's called an oxidizing agent, because it is the agent that is responsible for oxidizing. Causes the oxidation of another species, and the oxidizing agent itself is reduced. Oops, too far. 71. There, 73. Let's see if 73. All right, this is definitional. Seems to be a lot of these here in this one group. All right. When we balance an oxidation reduction equation, the number of electrons lost by the reducing agent must blank the number of electrons gained by the oxidizing agent. The number of electrons lost by the reducing agent, causing the reduction of some other, must equal the number of electrons gained by the oxidizing agent. First, I had to be careful. I mean, sometimes they can be tricky. The number of electrons lost by the reducing agent, is that true? Yes, the reducing agent causes the reduction of something else by transferring its own electrons, so that is true. So they must be equal in magnitude, opposite in sign. There we go. How about 75? Is it different? An electrochemical cell that produces a current from an oxidation reduction reaction is often called a galvanic cell, named after the Italian Galvani. What Galvani did was he took discs of different metal, two different metals. In fact, I think he used copper and zinc. And he just stacked them together. Right? And between each one, he had an acid-soaked piece of cloth. So let's see. I'm trying to remember which one is reduced and which one's oxidized. Zinc, copper, zinc, copper. Zinc is more reactive, so it should give up its electrons. So the electron flow is going to be like this. So when he completed the circuit here, you could, ask your friends, put one hand here and one hand here, and they'd get a shock. This is known as Galvani's pile. And it was the first instance of a battery. But we call it a galvanic cell. Now, actually, there are several cells here. Right? There's a cell and there's another cell stacked in sequence. When you stack them in sequence, the voltage that you get from one is additive to the voltage of the other one. So that's why lead-acid batteries in your car have 6 independent cells. Each one has 2 volts. Each one has 2 volts. So if you connect them like this, positive to negative, the total is 12 volts. But they have to be in series. So you would have positive to negative, positive to negative, positive to negative, so forth and so on. And that's how you get 12 volts out of a battery. Farm tractors very often have 24 volts, so they'll have 12 cells. Or diesel tractors, 24, sometimes they have 48 volt batteries. Some marine batteries have more volts than that. Okay, so let me see. Let me submit my answer here. 77. At which electrode do species gain electrons in a galvanic cell? This is a good question. So we're talking about the electrode where electrons are gained by that side. So you have an electrode over here, and electrons are flowing in this direction, right? So they can participate as a gain, right? Reduction is gain. So if the electrons are exiting here and reacting with something, then this is going to be the site of reduction. And what do we call the site of reduction? The cathode. Right? So that's where the cathode is located. Right? We got to come from somewhere. So let's say we got another. By the way, this is a half cell. That's another half cell. This is the cathode. And this comes from over here. So electrons are going into this one. And some, well, let's not make it the same one. Let's make it a different one. Y yields those electrons plus the oxidized species. So this is the oxidation side, and it's called the anode. Okay? So in every water heater, in every house, there is a rod of metal, sometimes zinc. That's a little expensive, usually aluminum. There's a rod sticking down into your water heater. It's especially important with our source of water because we have hard water and it will form scales. So what it does is, it's called an anode. It's called anodic protection. And the anode, this aluminum rod, reduces. And what it does is as it oxidizes, it contributes electrons to the solution, to the water solution, and prevents the formation of scale. I remember the first time I discovered, in practical terms, what that anode was all about. Well, as the aluminum is oxidized, it converts to some other aluminum compounds, right? Might be aluminum oxide, it might be something else, aluminum chloride, whatever. But it forms these little white granules, and they end up in your hot water. So any place that you use hot water, those little granules are coming out of your water. Well, it so happens that my dishwasher has a little metal screen in it. And it got to the point when we first moved into the house, it didn't take long, a month or two. I noticed my dishwasher wasn't working very well. At the bottom of the tub of the dishwasher wasn't filling up with water. So I took it apart and I looked in it, and that little screen was covered in those white crystals. So that's when I went down to the basement and pulled out the rod and found that it was almost completely eaten away. So the moral of that story is, when you move into a new house for the very first time, that rod is going to be depleted really fast because of other electrochemical reactions that go along with it. But after a while, and I think it has to do with the pipes in the house. If they're copper pipes, then you get that corrosion faster. But if in modern homes that now they're building them with plastic pipes, and you shouldn't have that problem. But in that case, it's a good idea to periodically pull that rod out and check it. You know, like once a year should be enough, and replace it periodically. Okay, let's see about this one. Is it different? 081, come on. There we go. The common acid dry cell battery typically contains an inert casing made of blank. 81, 081. So what's the casing of the typical dry cell battery made of? It's usually made of zinc. And that zinc forms one of the electrodes, right? In the middle, you have the carbon rod. It's just a conductor. The carbon doesn't participate. In here, you have your other reaction. So what happens to the zinc? Well, the zinc is oxidized. Right? The zinc yields plus two electrons. So where do they go? Well, they go out, electrons go out like this. And then the electrons come out here and undergo reaction in that matrix right there. So there has to be a porous layer inside here to separate the two. That way, this is the site of oxidation, that's the anode, and this is the site of reduction, that's the cathode. All right, so zinc is the metal. Okay, we're doing okay on time. Not that I was worried. Here we go. Let's see. This one has several parts to it. 85. In the following reaction, identify which element is oxidized and which is reduced. You know, this is getting old. I think we're going to skip this one. Well, let me see what the part B, maybe B gets more interesting. All right, iron is going to iron 2 plus. Right, so it has to be oxidized. Iron is oxidized. Which one is reduced? Well, you end up with an element over here, and it comes from a compound, so hydrogen must be reduced. So hydrogen as H plus is reduced. Iron is oxidized. Hydrogen is reduced right there. Okay. Now this is nothing new either. Calcium is oxidized, selenium is reduced. Oh, I picked the wrong one, didn't I? Selenium. Oh, maybe we better look at this one a little closer. I jumped the gun on that one. Calcium plus selenium yields calcium selenide. Okay, I did jump the gun. Calcium is going to be oxidized. Actually, I punched the wrong one. I meant to punch this one right here. Calcium is oxidized. This is 2 plus. This is 0, that's 0. And selenium is 2 minus. How do we know that? Selenium is a chalcogen. It's same group as oxygen, sulfur, selenium. So their preferred charge in this type of arrangement is a 2 minus. All right, so that was my mistake. I punched the wrong button. I meant to say this one. Oxidized and reduced. So let's go ahead with C. So this looks like a net reaction. How do I know? Because 2 plus and 2 minus is 0, and then 1 plus over here. But 3 plus and 3 plus is 6 plus. Right? So the charges don't balance. But the transfer of electrons will balance. The overall charges, that seems to be contradictory to our earlier statement when it says charges balance. Well, yeah, the charges balance when you include all the counter ions, right? There's going to be an anion here, there's going to be a cation there, and there's going to be something here. It's probably an acid. So it'll be an anion there also. But once you get all the charges together, then they'll balance. But all we're concerned about with this reaction is, are the electrons balanced? Right? And we have to assume, we're assuming this is a balanced equation. So actually we can do this one without writing it on the board. So which element is oxidized? Oxidation is loss. Who's going to lose electrons? Their charge would become more positive. Right? So iron 2 goes to iron 3 plus. Iron is oxidized. Right? So it's one of these two down here. So what is reduced? Well, let's look. What's chromium here? Well, we might have to do that one. Cr2O7, dichromate. 2 minus. So this is 2 minus, minus 2, minus 14 total. And we're going to hold 2 out. So we only have to balance minus 12. So plus 12 here, that means plus 6. So chromium is going from plus 6 to 3 plus, which means a gain of 3 electrons, right? Oxidation is loss, reduction is gain. So chromium 6 in this one is reduced to chromium 3 plus. Be sure I click the right one this time. There we go. Now, why is it saying I'm only partially correct? Oh, I was correct for C, partially correct for the whole group, right? Because I missed that one by clicking the wrong one. I'm not going to try another version. We're going to see if there are any more. Number one's worth looking at. 091. Let's see. Multiple parts for the following oxidation reduction. Metal with a non-metal. Identify which element is oxidized and which is reduced. Now here's another rule of thumb. In most cases, since nonmetals tend to prefer acquiring electrons because they're more electronegative, and metals tend to want to lose electrons, then my bet is that I can say, all right, a metal is going to lose electrons. That's oxidation. Potassium is oxidized, and nitrogen is reduced. Yep. See? So that rule of thumb paid off there. This one should also work. Aluminum should be oxidized and sulfur reduced. There we go. Oops. I clicked the wrong one again. I meant to click A. Aluminum is oxidized, sulfur is reduced. Okay, so it caught me. Potassium is oxidized, oxygen is reduced. Right? I did click the right button. There we go. And the last one. Calcium is oxidized, oxygen is reduced. Right here. There we go. Let's see. We don't have any more number ones, so we'll go back to the top and start on number twos. How about this one? Okay, we can still see. That's good. Balance the following oxidation reduction reaction that occurs in acidic solution using the half reaction method. Okay. This one's going to require some methodical, step-by-step action. And this one doesn't have a number, right? Because it's right, chem work balancing equations. So we just have to put it on the board and do it. Okay, we're going to balance this equation using the acidic half reaction method. ASO43 minus. So let me see. Let's start over here. I'm still centered. There we go. ASO4 2 minus? No, 3 minus. There we go. All these are aqueous except sulfur. That's no big deal. I'm going to leave that out so that so it doesn't take up a lot of room. ASO3 3 minus. Notice we went from 0. We went from 4 oxygens to 3 oxygens here. And then sulfur. Okay, so what do we do? First thing you do is oxidation numbers. Find out the oxidation state of each element so that you can tell which reaction is oxidation, which is reduction, before we split them apart. Right? So oxygen is -2 times 4 is -8, but we need to hold 3 minuses out for the charge. So we really only need to balance -5. So we need a +5 here. Okay? Right? Sulfur is the charge. There's only one element here. It's got a charge. That's its oxidation number. Over here we have 3 times 2 minus is -6. Hold out 3 minus 3. So now we're +3 here. And this is 0. which reaction is oxidation, right? Which one actually lost electrons? Sulfur. This ion lost 2 electrons to go to here. Right? So the oxidation reaction is S2 minus to S0. Oxidation. Reduction was what's left over. ASO4 3 minus. And I'm going to write this one here just so we can keep track of it. And then ASO3 3 minus. That's plus 3. Okay? Now what's next? We split the equations. Now we balance the elements. Right? 1 to 1, that's balanced. 1 here, 1 here, those are balanced. Then we go to oxygen. How do you balance oxygen? You balance it with water. So we have 4 oxygens here and 3 there, so we need another oxygen over here. There it is right there. 1 plus 3 is 4, 4. All right? We don't have anything to balance up here. It's just as it is. Now we've got these 2 extra hydrogens over here. How do you balance those? Well, you balance those in the acid method with protons. So we need 2 protons over here. Okay? Now we're going to balance electrons. Right? 2 electrons here end up where? There. 2 negatives here, 2 negatives there, no charge there. We're balanced. On this side, we're going from plus 5 to plus 3. Right? So we had to gain electrons. So we had 2 electrons gained on this side. Right? 2 negatives, a plus 5 makes a plus 3. Right? So now you look to see, are your electrons balanced? 2 electrons balanced. We can add the equations together. Right? So we have 2 electrons. We have the arsenate ion. We have 2 hydrogens. And we have a sulfur. Now over here we have 3 minus, a sulfur, plus a water, plus 2 electrons. Now you cancel common terms. Electrons are gone. They're balanced. That, same, there's nothing to cancel there, nothing to cancel there, nothing to cancel there. So which one looks like this? Well, let's look on the left-hand side. ASO4 3 minus, right? That one's there, 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 there. This one doesn't work at all. So it's one of these up here. How about 2 hydrogens? There's 2 hydrogens, right? No hydrogens there. There are 2 hydrogens. And there are 2 hydrogens. Right? But we also need sulfur, S2 minus. Right? We got one there, got one there, we got one there. And we have 2 electrons, 2 hydrogens, and AS. Okay, so this one and that one are candidates. Let's look on the other side. ASO3 minus plus water, but it's missing the sulfur. Right? This one has the sulfur. So this one must be the correct answer. Okay? That one took a little extra work. so let's see, where were we? Scroll up a little bit. And the next number 2 difficulty here. Okay, let's see. There we go. We got 3 of them. And I forgot the number already. 15. Let's see, 18.015. Okay, for A, what's the oxidation state of S8? It's 0. That's an element. All right. How about H3PO4? What is that? Well, if it's in solution, that's phosphoric acid. So what's the oxidation state of phosphorus here? Well, this one's +1, so that's +3 total. This one's -2, so that's -8 total. -5 overall, so this one must be +5. Come on. There we go. All right. How about this one? C. NaHSO4. Sodium, hydrogen, sulfate. The trivial name, that's the IUPAC name. The trivial name is sodium bisulfate. So you may see it both ways. So sodium is an alkali metal, it's +1. Oxygen is -2, so that's -8 here, +1 here. -7 total. Oops, I left out hydrogen, excuse me. So that's +1. That's 6. 6 minus. And then this has to be +6 to balance that. And then sodium fluoride. We don't even have to put sodium fluoride up here. Fluorine is -1. Sodium is an alkali metal. It's always +1. Wait a minute. Oh, fluorine, excuse me. Fluorine is -1. There we go. That's just the rule. Okay. That was 15. Let's see. 41. Oops. Multi-step. Choose the balanced equation for the following half reaction. All right, we can do this one pretty quick. What number was that? 41. All right. Iron. 0 going to 3+, correct? Oh, 2+, sorry. 2+. Okay, what's happened to iron? It's oxidized. When you oxidize something, the electrons for that one end up on the other side because it has lost them to the products. So for this half reaction, those 2 electrons are there. Right? So that means this one right there. The next one is a little trickier. If we go titanium 3 plus. I'm leaving out the aqueous just for convenience. And we go to titanium 2 plus. What's happened? It's decreased number from 3 plus to 2 plus. Right? It had to gain an electron. So titanium 3 plus had to add an electron to get to 2 plus. How about selenium? 2 minus. And it goes to selenium solid. That's 0. So it had to lose 2 electrons. Right? Go from -2 to 0, you have to get rid of those 2 negatives so that now your protons and electrons will balance. So those 2 negatives end up over here. And the last one, zinc 2 plus. Becomes zinc metal. You have to add 2 negatives to balance those 2 positives and give you a 0. So let's see, 2 electrons plus the zinc 2 plus yields zinc metal right there. Okay. That was 41. Let's scroll up a little bit. There we go. 43. All right, this one, all right, we got several equations to be balanced in acidic solution. It looks like acidic, acidic, acidic. They're all acidic solution. Okay, so we can use the same method for each one. The only way to get good at this is to do a lot of them. So we're going from chloric acid to chloride ion in solution. And let's see. The balanced equation. Okay, they want us to go the whole route. All right. Actually, this is only the half reaction. Oh, it says that right there, doesn't it? The half reaction. So we're only going to balance the half reaction. HClO3 and Cl minus. What number was this? I forgot already. 43. All right. So for the first one, we've got HClO3, and then Cl minus. Okay. So what type of reaction is this? Well, let's see. That's a -1. What is this chlorine? Well, let's see. This is -2, -6 total. This is a +1. So we have a -5. This is a +5. That's a reduction. Right? So we're going to put electrons on this side. Oops. Erased the wrong thing. There we go. All right. So chlorines are balanced 1 and 1. Now we do oxygen. We need 3 oxygens. Correct? Now we need to balance 6 hydrogens. Okay. Now we're going to balance the electrons. So how many electrons do you have to add to go from a +5 to a -1. Well, it takes 5 of them to go to 0, and then 1 more to go to -1. Right? So it's 6 electrons. Like that. And that should be the answer. 6 electrons, yep. 6 hydrogens. Oh no. Look at the mistake I made. There's already a hydrogen here. We only need 5. Now we have 6. So you have to be really careful. I even make mistakes. 6 electrons, 5 hydrogens, HClO3. So it could be this one. It could be this one. How about this side? Only 1 chlorine and 3 waters. This is the one right here. There you go. Now see if I can do a little better with this one. B. NO and N2O. NO and N2O. Okay. That's a 2-, so this one has to be a 2+. This one is a 2-, but this one has to balance that 2- with a 2+ and share it between 2. So each one is +1. So we went from a 2+ to a +1, which means we added an electron. Nitrogens are not balanced, right? So I jumped the gun. Too soon for electrons. We need 2 of these. There we go. Now that we have 2 of those, 2 of these, then we can balance the electrons. Well, let's do the electrons last. How about oxygens? We got 2 oxygens here, 1 there. So we need another one here, like that. And then we need those 2 hydrogens. Now let's do electrons. So we have a +2 to balance there, right? Because you've got 2 of those. And we have a +4 here, right? 2 times 2-, 2+. So we need to transfer 2 electrons. We have to add 2 electrons here. So that should be it. Except I didn't do it right. What did I do wrong? Oh. Here's what I did wrong. 2 oxygens. There's only 1 here. Just a minute. Let me see. Do that first. Now we have 2 oxygens here and 1 there. We need 1 more. That gives 2 hydrogens. And we have, well, that should be right. Oh, I wrote it wrong. Now I'm looking at the wrong one. Excuse me. I'm looking at C instead of B. B, NO to N2O. Okay. So we've got 2 electrons, 2 NOs, 2 hydrogens, yields an N2O and 1 water. This is it right here. See how easy it is to get confused. All right. Now the next one, we're going to NO2 to N2O. Right? We know this one's +1. We just did it. This one, though, is -4. 2 times -2. So this one has to be a +4. +4 to +1 means we need to add 3 electrons for each nitrogen. But we got to balance nitrogens first. 2 nitrogens means plus 8 goes to plus 2. So we need 6 electrons. Okay. Now we need 2. We got 4 oxygens here, 1 there. We need 3 oxygens here, which means 6 hydrogens. Okay. So now we have 6 electrons, 6 hydrogens, 2 NO2s, then we have an N2O, N2O, and 3 waters. So it should be this one right here. There we go. One more. All right, let's make some room for D. All right, D, ClO3 minus, and that's going to HClO2. Okay, that's a 2 minus, so it's 6 minus here. Got to hold 1 out, so we need to balance 5 minus, so that's a 5 plus. Okay, this one is 4 minus 4, and this one is a plus 1, so that's a minus 3, so we need a plus 3 here. Okay. All right, so what are we doing? We're going from a 5 plus to a 3 plus, which means we have to gain electrons. Chlorines are balanced. Oxygen, we need another oxygen over here. All right. So how many hydrogens do we need on this side? Well, there are 2 here, but there's 1 there. So we actually need 3 hydrogens. Now electrons. So we need to add 2 electrons. Okay, that should be it. 2 electrons, 1 chlorate ion, and 3 hydrogens. And then HClO2 and a water. Okay, those are the same. What's the difference here? Ah, hydrogens. Okay, that's 5 hydrogens. We only need 3. There we go. Okay. That was 43. And we're still level 2, I assume. Yep. How about this one? So let's see. I bet these are these were reductions. These were all reductions. I bet these are all oxidations. So let's see. What's the iodine here? Well, actually, you've got 2 different iodines. The iodide ion is one of the most easily oxidized species. Choose the balanced equation of the following oxidation reduction which takes place in a city. Okay. This one might be a challenge. What is number 47? Let me see if I can do this one without stepping all over myself. All right. So we got IO4 2IO4 minus. Yep. And then we have iodine. And then we are going to have there we go. Now we need to balance what? The iodines first. There's one, there's one, there's two. Okay. What about, there's a -1. What's the oxidation state of this one? Right. This is -2 times 4 is -8. Hold one out is -7. This is a +7. Correct? So this looks like we're going two different directions, doesn't it? This, we're going to have to split this one. Into oxidation. So what's oxidized? Well, this one is oxidized because it goes from a -1 to a 0. So we're actually going from here to here. And the reduction is going from this one with a +7 to this one. That's odd, right? Is this a disproportionation? Actually, it's disproportionation in reverse. Okay, so we got our separations here. Balance this one. We need 2 of these, correct? 2. We need 2 of these. 2 iodines. Okay. No oxygens or hydrogens here. We got how many? 8 oxygens here. Right? So we have 16 hydrogens there. Now we can balance electrons. So if this one is going from -1 to a 0, each iodine has to lose 1 electron. But we got 2 electrons. So we're going to lose 2 electrons to get to that place. This one is going from +7 to 0. So it gains 7 electrons for each iodine. From +7 to 0. But we got 2 of them. So it's 14 electrons, correct? Okay. Now let's see. We got 8 and 16 hydrogens. Okay. They're balanced. Now we need to do something so that the electrons balance. We have 14 here and only 2 there. Got to multiply the whole thing through by 7. So now we have 14. We have 7. And we have 14 electrons. Now we can add them together. Let's cancel some things before we do. Electrons cancel. Right? How about iodides? Nope. We can add these together, and we got water, so we can add the rest of them. So this is 2IO4 minus plus 14 iodines plus 16 hydrogens, and then 7 plus 1 is 8, and then 8 there. Okay? Notice we've got odd, even numbers. 2, 14, 16, 8, 8. We can reduce this further. IO4 minus plus 7 iodines plus 8 hydrogens yields 4 I2s plus 4 waters. There we go. Now can we find that one? There's an IO4. Yep. 7 iodines. So it's either this one or this one. 8 hydrogens. It's probably this one. 4 I2s and 4 water. It's this one right here. Okay? That took a little work, didn't it? Oh, we're still on 47. Now we're going to go to B. Put these out of the way. Okay. So B is what? MnO4 minus, the manganate ion, plus iodide yields what? Manganese 2 plus and iodine. Okay. So this one's going from a minus to a 0. Right? That means it was oxidized. It lost an electron. For each iodine, it lost 1 electron. Right? So that's the oxidation. Going from here to here. Okay? That means the reduction must be MnO4 minus 2Mn2 plus. All right. All right, so let's find out what that is. That's 2 plus. No big deal there. This is minus 2 times 4 is minus 8. Hold out 1 minus 7 that we need to balance. So this is plus 7. Okay. Here we go. Now, balance the elements first. Are you still here unless you click here? You'll be signed out. Click here. Yep. Okay, so we need 2 of these. That's done. Got 1 of these, 1 of these. That's good. Now we need to balance oxygens. We got 4 oxygens here. So we need 4 oxygens here, which means 8 hydrogens. No hydrogens there. So we have 8 H plus. Now we balance electrons. We went from a minus to a plus. That means we lost an electron. It went over here. But there are 2 of them. Okay? This one we went from plus 7 to 2 plus. That means we gained 5 electrons for each manganese. And that's it. Now we need to reconcile. That's a 2 minus, this is a 5. That's 2 electrons, this is 5. Odds and evens. The best way to handle that is to multiply 1 by 5, this one by 5, and this one by 2. Cross multiply. So this one's by 5, and this one is by 2. Okay, so this one's going to be 10 iodides, yields 5 iodine molecules plus 10 electrons. This one's going to be 10 electrons plus 2 MnO4 plus 16 hydrogens, 2 manganese 2 plus ions, and 8 waters. Okay, so we've got this one and this one to combine. So there's 10 electrons. Okay. No hydrogens or waters up here, so there's nothing we can cancel. So we just add them together. On this side, we have 10 iodides plus manganese O4 minus plus H plus. Right. Oops, my mistake. I was adding the wrong equations. This is a 2. And this is a 16. Now 5 I2s, 2 Mn2 plus 8 waters. Okay. 10, 2, 16, 5. We can't reduce it any further. So let's look for this one. Let's see. 2 MnO4s, there we go. It's one of these. Then 10 iodides, 16 hydrogens, 5 iodines, 2 manganese. That's it right there. Okay. I'm going to skip this one. Besides, it's easy. Notice you got no oxygens, no hydrogens here. This is going to be really, really simple. So I'm going to let you do that one. After I... Oh, let that one ring. And let's see if we can find something new. Maybe we can find one balanced in basic solution. That would be a good test. Let's go back up. And let's see, here's another 2. Cell reactions that occur in lead storage automobile battery. This one might be worth doing, actually. It's a practical one. Okay, so a lead storage battery has 2 different plates. One is made of lead, pure lead. The other is made of lead oxide. Lead 4 oxide, as a matter of fact. And what it produces is both of them are converted to lead sulfate. Okay? There we go. Now, this all takes place in sulfuric acid. But if we just balance that one by our method, well, where's the sulfate going to go? Well, the sulfate is a product over here. It has to be a reactant over here. So we have to have H2SO4 on this side to provide the sulfate. All right? And the hydrogens, where are the hydrogens going to go? the hydrogen is going to produce water. So it should look something like that. But that's not balanced yet. It's possible to balance this without doing the electron transfers, but we probably should. Right, so which one is, well, this is 2 plus, this one is 4 plus, and this one is 0. So the oxidation reaction is going from 0 to 2 plus. So we're going to have lead yielding lead sulfate. And then the reduction is going to be lead oxide yielding the same product. Okay? So we got one lead, we got one lead, that's good. Actually, we're going to have H2SO4 on this side and H2SO4 on this side. We don't know where the water goes yet. Right. So we just leave it alone. The water is something that we're going to add in our balancing anyway. But we do have this to begin with. All right. So the leads are balanced. We got sulfates balanced. We got hydrogens here. But we also have an oxygen there. So we want to put another oxygen over here, actually 2 of them. Right? That gives you 4 hydrogens there. We've got 2 hydrogens here, so we need 4 more hydrogens there. But that gives you 2 sulfates. This is not going to work. Here's what we're going to have to do. This is 2 plus, this is 2 plus. We're going to have to do it this way first, and then incorporate the sulfates afterwards. Because the sulfates are not undergoing any change, right? They're going from sulfate to sulfate. But the oxidation reduction is with the leads. Okay, so let's do this again. There's one, there's one, there's one, there's one. This one needs an oxygen, 2 oxygens, and that makes 4 hydrogens. Okay, now we can balance electrons. This one had to lose 2 electrons. This one had to gain 2 electrons. Okay. Let's see. Yep, electrons are balanced. Now we can just add these together. So this is lead plus lead oxide plus 4 hydrogens. Electrons cancel. And this is 2 leads. Plus water. Okay? Now we can incorporate our sulfates. Right? So this one is going to take 1 sulfate for each one. Right? 2 sulfates, because sulfate is a 2 minus charge, that's a 2 plus charge, that balances. Okay? So now you need sulfate on this side, and you're going to incorporate sulfate on this side as sulfuric acid. But let's put sulfates over here just as is. That's an anion, 2 of them over here, 2 sulfates over here. Okay? Now, we've got that one taken care of. We put our sulfate over here. Let's combine that sulfate with these hydrogens. if we need 2 hydrogens for every sulfate, and we have 2 sulfate, we need 4 hydrogens. So this one combines with this one to make 2H2SO4. So there's our balanced equation. It was a little bit different than the standard procedure, simply because we excluded the spectator first. Then we put the spectator back. That's the sulfate. So if we've got 1 lead and 1 lead oxide, 1 lead and 1 lead oxide, and 2 sulfuric acid, there we go, and then 2 lead sulfates and 2 waters. This is the answer right here. Okay? I hope that wasn't too confusing. I was kind of thinking out loud as I went anyway. All right. What species is oxidized? Well, the lead becomes lead 2+. Right? What species is reduced? Lead 4+, or lead oxide, becomes lead 2+. Now it's oxidized. Now that's reduced. This is oxidized, excuse me. Lead is oxidized. Here we go. About to click the wrong one again. Lead is oxidized. Lead oxide is reduced. There we go. And then why can a lead storage automobile battery be recharged? Well, the reaction can be reversed. All you have to do is pump electrons into it and just run the oxidations and reductions backwards. This is what we call spontaneous. This is spontaneous reaction. You just put them together and they go. To make them go the other direction, you have to supply energy to drive them in reverse. So let's see which one. This reaction can be reversed by electrolysis of the mixture. No. You're not electrolyzing lead and lead oxide. You're electrolyzing lead sulfate. Here, right? To go this side backwards, you're electrolyzing a mixture of water and lead sulfate. There we go. That's the correct answer. All right. Let's see. We got another bunch of number ones we've already done or skipped. We got another about 45 minutes. So let's see if this one's worth looking at. The pressure on electrons to flow from one electrode to the other in a battery is called the blank of the battery. That's the voltage of the battery. Think of voltage as a push. Okay. There we go. Now, let's see. Scoot that back a little bit. There. All right. I didn't put that one on the board, but that's all right. The next one, 083. Although aluminum is reactive, pure aluminum ordinarily does not corrode severely in air because of a protective layer of blank builds up on the metal surface. Right? That's true of all metals that are extremely reactive in oxidizing environments, like pure oxygen. What they do is they react with the oxygen so fast that it forms a skin that protects the underlying metal. And in this case, it's aluminum oxide. Chromium does the same thing. Only chromium is used in stainless steel to do the same thing, right? The iron in the steel would typically convert to iron oxide and eventually just corrode the metal to pieces. But with chromium in there, in sufficient amount, it forms a skin on the surface. So you can scratch stainless steel and it instantly forms that seal. There's one other thing that we don't talk about is the volume of the oxide versus the metal. So if you go from iron metal to iron oxide, the volume of this iron increases dramatically. So when you form rust, it tends to take more room, right? So wherever the rust forms, it tends to balloon out and flake. That's why when you see an old tractor or an old car sitting in the field, and you look at the rust spots, you see they're kind of flaky, right? It'll flake away, and that exposes new metal underneath. And that means it just continues to rust until it's all gone. Whereas with aluminum, the aluminum oxide, I should put oxygen here. Let's see. Oops, 3. No, that's 2. And 4. There we go. Aluminum oxide, okay, with oxygen, and it should do the same thing. Let's see, 3 oxygens, 2, we need 2 and 3, and then 4. So this aluminum, forming the aluminum oxide, the volume of this aluminum oxide is not that much different than this one. The same thing with chromium. If you do chromium and chromium oxide, which would be something like that, the volume occupied by either of these oxides is not much different than the metal. So the crystal matrix that forms from these oxides is protective. It sits on the surface and it doesn't flake away because of the expansion. Well, the other possibility also is that when these aluminum oxides and chromium oxides form, they don't form in a solid crystal matrix that causes them to flake when they expand. Aluminum and chromium form a much finer grained matrix, which sort of fits together, and if they do expand, they expand outward and they seal rather than flaking. Right, those two possibilities. Since I'm not a metallurgist, a metal engineer, my explanation is probably incomplete. How about 089? Choose the balanced equation for the following reaction in acidic solution. Now, we've done one of those. How about this one? Assign oxidation states to all the atoms in PBr5. We can do that one without putting it on the board. Bromine is -1. Right, so that means phosphorus has to be +5. Right there. How about this one? Well, sodium's 1, fluorine's -1. How about barium chloride? Did we do this one already? Sure, deja vu. Chlorine is -1, barium is +2. Barium is a as an alkaline earth. Right? So this is a foregone conclusion. How about, what is this? Tellurium iodide. So we kind of have to look up where is tellurium. Tellurium is right next door. It's between mercury and lead. Right? It's right here. Right? So it has a couple of possible oxidation states. So we're going to have to calculate that based on iodine as a -1. So if iodine is -1, tellurium has to be a +1. All right. Okay, let's see. How about this, number 2? We've still got time. This is 096. All right. Now we're going to do ions, oxidation states for atoms in ions. Bi, that's bismuth. Right? If you've ever taken Pepto-Bismol, you know, the pink stuff for an upset stomach or for diarrhea or whatever the case may be, you have swallowed bismuth. It's not this form, but it's still bismuth. Bismuth chloride +1 ion. Okay? If this is a -1, and you have to have a +1 up here, that means this one has to be a +2, because a +2 and a -1 is a +1. Right? So bismuth is a +2. Oh, wait a minute. What am I thinking of? Chloride. My mistake. So this would be a -2, and this would have to be a +3. +3 and a -2 is a +1. So it's a +3 and a -2, -1. +3, -1. There we go. How about the phosphite ion? Okay, -2, -6 total. Hold 2 out. So that means we have to balance a -4. So a +4 for phosphorus. What did I do wrong? Am I looking at the right one? Oh, 3-. There we go. So +3 and a -2. +3 and a -2. There we go. All right, nitrite. And we do this one over here. Be sure I write it correctly this time. NO2-. All right. So that's a -2 for oxygen, a total of a -4, but we got to hold 1 out. So that's a -3. This has to be a +3. So a +3 and a -2. Okay. And the last one. Mercury HgI3-. HgI3-. Iodine's going to be a -1, -3 total. Hold 1 out, -2. Mercury's a +2. So it's a +2 and a -1. There we go. It's interesting, if you know about mercury, that whenever you see mercury by itself, it's always a +2. if you see mercury paired, Hg sub 2, it's always a +1. That's just the way mercury behaves. But we calculated it this time. '97. We've done one like that before. Let's see about 99. Choose the balanced equation for the following half reaction. So in this case, we're oxidizing. I'm going to skip that one too. These are acidic solutions. We've already done acidic solutions. They would be somewhat challenging. How about this one? This is interesting. This is the last difficulty level 2. Comes in 2 parts. So this is, how soon we forget, 103. Okay, let's look at this sketch. We have, based on this reaction, magnesium plus 10 ion yields magnesium 2 plus 10 metal. Okay. So we have this galvanic cell, and we have to choose between these two, right? That's kind of small. Let me see if I can blow it up a little bit so we can see it better. There we go. That's a little bit better. So which one of these actually would separate, excuse me, you have to think of a galvanic cell. Its half cells separate the oxidation reaction from the reduction reaction, just like we would do here to balance this equation. So which one's the oxidation, which one's the reduction? Well, in this case, it's not important, because the difference between these two is the structure of the half cell. If this is 10 metal, then there should be 10 ions in solution, but they're not. They're magnesium ions. So that one cannot be. It will not work. This one will work. Magnesium and magnesium ions, 10 and 10 ions. That one is the correct answer, right? And that's all we have to do to solve this one. We don't have to say which side's oxidation, which one's the cathode, which one's the anode. We just look at the structure and decide which one is the correct one. Right, there it is. Now on this one, once we've decided that that's the correct structure, which metal is reduced and which is oxidized? Well, now we go back to the equation. We're going from 0 to 2 plus. That is an oxidation. Lost electrons, right? This one is a reduction. It gained electrons to go from +2 to 0, right? So 10 2 plus is reduced. That's correct. Magnesium metal is oxidized. That's correct. Oh, we got a C. Didn't see that one coming. Okay. What half reaction takes place at the anode, and what half reaction takes place at the cathode? Okay. Which one's the cathode? The reduction. This is the cathode. That makes this one the anode. So it says, first of all, what reaction takes place at the anode? The oxidation of magnesium, right here, and it loses electrons, so electrons have to be on this side. There are two of them. That's the anode. There's the anode right there. Cathode, the 10 adds electrons. So 10 plus electrons, this one. This one's at the cathode. There you go. All right. Now, let's see. Let's go back up and see if there are any. We've done. Was that 2s? Yeah, 3s. So we got a 3 here. Assign oxidation states for the elements listed in each of the following compounds. Okay. That doesn't seem like a very high difficulty level, but we'll tackle it anyway. But what's the oxidation state for lead in lead oxide? What number is this in? Oh, it doesn't have a number. So lead, there we go. This one's 2 minus. That means -4 here. That means +4 there. So lead has to be +4. There. Carbon, CO2. This would be 2 minus, -4 total, so this is +4. Carbon is a +4. Nitrogen in NH4 taken twice, cerium sulfate. Ammonium, cerium sulfate. All right, here's the easy way to do this one. Notice that the nitrogen is contained only in this polyatomic ion, NH4. So if we say NH4 plus, now we can determine the oxidation state of nitrogen without messing with the rest of the molecule. So this is 4 pluses here. We have to hold 1 out for that plus. So now this is 3 minus. So nitrogen is a -3. How about sulfur in this one? We can do the same thing with that one. Sulfate, right? 2 minus times 4 is 8 minus. Hold 2 out is 6 minus. That sulfur is 6 plus. There it is. And bromine, we got to do the whole molecule for this one. Well, bromine, we have to take it as a -1. We don't have any choice. Cobalt is a transition metal that could have more than one charge. And the more electronegative is the one that fixes the charge. So bromine has to be -1. Okay? That was level 3. Here's another level 3, 29. Let's see. You know, maybe I can reduce the size of this one again. $29. Okay, let's see what that says. Which is reduced. All right, that's repetitive. We've already done those. Ones like them. I want to find something that's unique in the remaining, the time we have remaining. Here's another 3, 95. Let's see if it's different. 095. It's got several parts to it. Right. I hope the subsequent parts are more difficult than this one. Chlorine is -1, aluminum +3. How about this one? Okay, now we're getting a little more difficult. Oxygen is a -2, right? Scandium is what? Well, if this is a 2-, then that's 6- plus. We need a 6+ over here, but each one has to be a 3+ because there are 2 of them. So 3+ and 2- would be the answer to that one. How about this one? Gallium sulfide. Okay, this one, sulfur is in the same family as oxygen. And when it's in an ionic combination, it behaves like oxygen. It's a 2-. So that's 6- total, which means this has to be 6+ or 3+ each. So this one also is 3+ and 2-. Oh, we got another one. All right, this one's gallium and silicon. Gallium and silicon. So 3 here and 4 there. All right, this one takes a little. Silicon is in this case, silicon is going to behave like a nonmetal. Right? Silicon is right here. Let's see, right there underneath carbon. And you remember the dividing line goes underneath the boron down like that stair step. So silicon is just barely a nonmetal. When nonmetals are combined with metals, they behave, but their electronegativity is dominant. So when silicon is with gallium as a metal, then silicon tends to draw electrons to itself and make itself the negative side. So when you look at silicon in its position in the periodic table, if you work from left to right, -1, -2, -3, it's going to be a -4. Silicon will be a -4 in this case. So that's a -12. +12 means this one has to be a +3. And that also is consistent with where gallium is located. Gallium is right underneath aluminum. Aluminum is always 3+. So gallium would tend toward 3+ in a metal-nonmetal interaction. So that's good for both of them. They're consistent. +3 and -4. Well, why does it say that? Because it clicked the wrong one. I wanted +3 and -4. Right? That's what it says. +3 -4. Okay, so I was right. The system clicked it wrong. I'm not going to take responsibility for that one. All right. Let's see what else we got. 3. Are there any 4s? There's a 4. There are no 4s up here. There's only one 4. So let's see as we close out if this 4 is really as difficult as they say it is. Multiple levels. Carbon compounds containing double bonds called alkenes react readily with many reagents. That's true. In the following reaction, identify which atoms are oxidized and which are reduced, and specify the oxidizing and reducing agents. Okay, this is a challenge. Simply because, let's see, 87. We have to modify the rules for oxidation state in order to incorporate carbon. Okay. Now, I'm going to give you these rules. I'm not expecting you to, well, let's see, there is one question. Maybe we'll get to it in the review document, but I'm going to give it to you now, and you can chew on it. So when you have carbon by itself attached to some other, whatever it happens to be, then you take the oxidation states of these others and then balance the carbon against it. When you have carbon with carbon, these are identical to one another in electronegativity. So they influence each other not in the least. So you would take these three and balance them against a neutral situation. For instance, if we have chlorines over here, and we have hydrogens over here, okay, we would separate them because the carbons don't contribute to one another at all. They don't affect their oxidation states. So this is a -1, so that's 3 minuses. That means this carbon has to be a +3. All right? Hydrogen in covalent compounds is a +1. So all these together is +3. That means this carbon is a -3. Okay? So let's take these examples. And that also works for double and triple bonds. When you have that first one, this one, and that one, and then you have these two hydrogens. Right? When we write organic compounds, the hydrogens that follow the carbon are attached to the carbon, not attached to this carbon, not to the other carbon. The bond, the double bond, is between this carbon and that carbon. Okay? So if we wrote it like this, those carbons are equivalent. So we just need to do one of them, right? So this is +1. That means a +2 total. That means this carbon is -2. This one is -2. Okay? So this chlorine is a 0. We know that. And then the CH2, Cl, CH2, CH2, Cl. So each one of these carbons is going to be equivalent. They're bonded to the same atoms. So this one is 2 pluses for those two hydrogens and a -1. So that means this carbon has to balance a 1 plus. So it means it's a -1. There you go. So we're going from a -2 to a -1. The carbon is being oxidized. Right? Carbon is oxidized. Here it is. There we go. What about chlorine? Well, chlorine is going from a 0 to a -1. It's being reduced. Chlorine is reduced. Okay? Now, if chlorine is reduced, that means it is the oxidizing agent. There. And the alkene is the reducing agent because it is being oxidized. Let's see if I got it right. Okay. So I gave you a new set of rules for oxidation states when you're dealing with carbon. And we'll probably, I think there's one review question. Maybe there is in the review document, and we'll look at that one Thursday. So I think that's probably it. That was level 4, and I don't think there are any more. Yep. Looks like we're all done.